Hello. In this tutorial, we're going to talk about game loops and what they are and why should you use them. A game loop runs continuously during gameplay. Each turn of the loop processes user input without blocking, updates the game state, and renders the game. It tracks the passage of time to control the rate of gameplay. When talking about different game programming patterns, it's not possible to avoid quintessential example, the game loop pattern. Almost every game has one, and you will be hard-pressed to find two which are exactly the same. Modern games under the hood are not all that different from the old text-based adventure games. Only instead of text commands, the game takes user input events to trigger blocks of code that advance the game. One of the biggest differences from other user interface applications is that in games the animations keep animating, particle effects keep swirling, and monsters keep attacking your character even without user input. These process input, update, and render cycles take a fraction of a second, and in the end of the loop cycle, a frame is rendered for the player to see. Since the process takes such a small amount of time, frames per second is a good measurement of the game's speed on the device. A game loop has two key pieces: non-blocking user input and adapting to the passage of time. Input is straightforward. The important part is how the developer deals with time. Considering that there are near infinite number of platforms that games can run on, and any one single game may run on quite a few. So how it accommodates that variation is key. The two factors that influence the speed of the game are the amount of work to be done in a cycle and the speed of the underlying platform. Early video games had the luxury of being made exclusively for specific hardware. Therefore, they were carefully programmed to do just the right amount of work to make the game render at the right speed on that platform. The only advantage of the fixed time step with no synchronization approach is its simplicity. You can see the most basic pieces of the game loop in the scheme. The process input method handles any user input since the last call. Update advances this simulation of the game by one step, and render draws the current game state on the screen. As game speed is dependent on hardware and game complexity, it will run fine on the target platform, but if run on different hardware, it will speed up if the hardware is better or slow down if it's worse. Fixed time step with a synchronization is still as simple, just a tiny bit different from the previous approach. The idea is to keep the game away from speeding up too much by adding a line of code which adds a delay in the end of the loop. If your device has updated and rendered the step quicker than expected. Also, a good idea is to consider using it for mobile games, as by adding that delay, you're effectively limiting the frame rate, which can save power. Limiting the amount of frames this way makes the frame rate smoother, and therefore the overall game experience more reliable. Implying if the hardware can handle the game well. But if the hardware can keep up with the game, it will still slow down, as it was the case with the previous approach. A variable time step. Imagine you're playing a game where one step is processed quickly and the other one slowly. This is an example of a variable time step. Say we've got a two-player network game, and Fred has some beast of a gaming machine while George is using his grandmother's antique PC. A bullet is flying across both of their screens. On Fred's machine, the game is running very fast, so each time step is tiny. We cram, for example, 50 frames in the second it takes for the bullet to cross the screen. George's machine can only fit in about 5 frames. This means that on Fred's machine, the physics engine updates the bullet's position 50 times, but George's only does it 5 times. Most games use floating point numbers, and those are subject to rounding error. Each time you add two floating point numbers, the answer you get back can be a bit off. Fred's machine is doing 10 times as many operations, so he'll accumulate a bigger error than George. the same bullet will end up in different places on their machines. Fixed update time step variable rendering. To find a solution for the variable time step problem, we must look at each part of the engine, what each part of the engine is doing. The one part that isn't affected by variable time step is rendering. It will render things wherever they are at the rendering point, no matter how much time has passed. The solution would seem to update the game with fixed time step and allow flexibility with rendering. We still measure the amount of time that has passed, and this is how much game time needs to be rendered to allow the game to catch up. Now there's just one issue left, residual lag. This happens because we update the game at a fixed space of time while rendering whenever we can afford to. Fortunately, the developer knows exactly how far between update frame he is when rendering. It's stored in lag. Having that in mind, he just needs to bail it out of the update loop when it's less than the update time step, not when it's 0. Code explanation can be seen in the notes. There are 3 common ways to use the game loop. One of them is the platform event loop. Using it is quite simple and saves you time. Apart from that, it is optimized for the platform. But the event loop makes its own decisions when it comes to calling the code, as you cannot control it. It can be both smooth and frequent or not. Unfortunately, most application event loops are not designed to carry on with games, which makes them unusable. The other way is a game's engine loop. The good thing is that it is already written, so you don't have to. If you write your own game loop, it can get extremely complex because even minor bugs can have a massive impact on your game. This is why using game engines loop might be a good option. On the other hand, if you lose control over the process when it comes to fitting something which is not perfectly implemented by the engine. The third way is to write your own game loop. It gives you total control, so you can make it do whatever you want to. But there is a catch as well, as you need to interface with the platform. It can get extremely difficult to make the loop stable. Power management. While power consumption is mostly a non-issue for desktop computers and most consoles, mobile gaming requires power management. Most people won't play your game if it drains their phone batteries in 10 minutes. Therefore, you must make a decision between letting the game run as fast as possible or limiting the maximum frame rate. Letting the game run as fast as possible makes the game look better and, as an added bonus, heats up your lap. This might be desirable in cold, harsh weather of Scotland, but further south it can be an inconvenience. Limiting the frame rate, on the other hand, has an impact on graphic fidelity, so you have to make a decision on what the limit will be. The standard limits are 15, 30, or 60 frames per second. The comparison of the frame rate limiting impact on graphics quality can be seen in the video. Thank you for your attention.